So this video discusses about the superposition principle of electrostatic force in one dimension. So what is it that the superposition principle in one dimension of electrostatic force talks about? Now the emphasis is that, let's say we have the system of, let's say, charges in a one dimension, that is along x-axis or y-axis. Let's say this is a charge 1. I'll call it as a negative charge, and let's say this is charge 2. I'll call it as, let's say, a negative charge as well. Let me call it as a positive charge. Let's say it is given as the positive charge, and we have, let's say, a charge 3. Let's say I'll call it as, should be a negative charge, and we should also have, let's say, another charge, and but let me just have to use the 3 charges here. It will be enough. So let's say the distance between the 2 charges, charge 1 as well as the charge 2, it is given as, let's say, A, and the distance between charge 3 as actually charge 2 as well as the charge 3, it is given as, let's say, given as, should be B. So now, according to the Newton's electrostatic law, it is states that the like charges repel and unlike charges attracts, and it is after the actually a Coulomb who invented how one can be able to find the magnitude of either repulsive force and also attraction force. So using the Coulomb's law, we can be able to find the force of attraction and the force of repulsion that Isaac Newton did not specify. And that particular force is the same for all charges, basically for the 2 charges, according to the Newton's third law of motion. Let's say we have, this is a charge 1, a positive charge, and let's say we have the 2 charges being some distance away from one another with a separation distance given as r. Let's say this is the charge 2, and that should be given as the negative charge. So since these are unlike charges, there is a force of attraction. So each force, actually each charge is going to experience the force of attraction towards one another. And the force, now, and the force in which a charge 1 is going to experience and are due to charge 2 will be towards this direction, because charge 1 is going to experience the force and applying force towards this charge, and we'll call it as F12, meaning the force charge 1 experiences due to charge 2, and likewise the force in which actually charge 2 will experience due to charge 1 will be given as, let's say, towards this direction. We'll have it as F21. So in this case, you can see that these forces are the same, but they differ in the direction. So according to the Newton's third law of motion, the force actually F21 is the same as the negative, the force, I should say, the force F12 is the same as the negative actually force T1. This is according to the Newton's third law of motion. So keep that in mind. So the 2 actually charges experiences the same force but in opposite direction. And let's say this is, I'd say, a positive charge. What would you say about the forces that the 2 charges will experience? So now the 2 charges are going to experience the repulsive force, and that is to say, let me give it this way. Now the 2 charges are going to experience the repulsive force, in the sense that the force F1 will experience will be towards this direction, away from F2, away from the charge 2, and that will be given as F12. And the force charge 2 will experience due to F actually, and the force charge 2 will experience due to actually charge 1 will be towards the other direction. That will be given as towards this direction, F21. So principle remains the same. You should have to understand that F21 is the same as the negative, I should say negative F12. And this is according to the Newton's third law of motion. So that's the principle we should have to understand. That's the principle you should have to understand behind the Newton's electrostatic law and sort of. Now, what is the superposition principle in one dimension? Now, we have the system of the three charges in one dimension, that is along x-axis. You should have to understand that, let's say we have the charge of interest, let's say the charge 1. Looking at the charges that are in the system, charge 2 as well as the charge 3. You know, this actually charge 1 experiences the force due to charge 2 as well as the charge 3. And now the summation of those actual forces a charge 1 experiences due to the other actual charges, now that's what corresponds to what we call the superposition principle. And now for this case, you should have to understand that a charge 1 experiences the force due to charge 2 and also due to charge 3. And likewise, charge 2 experiences the force due to charge 1 as well as the charge 3. And also charge 3 experiences the force due to charge 2 as well as the charge 1. So now the summation of those forces acting on a specific charge, that's what corresponds to the superposition principle. And now since the charges are in one dimension, then we call it as superposition principle in one dimension. So let's see on how we can go over on the superposition principle in one dimension as we have it here. So let's have an interest to look at the net force acting on charge 1 due to the other charges. So in terms of the vector notation, we'll have it as F1 net. So what is this trying to tell us about? It means the summation of the net force acting on a charge 1 due to the other charges. So now which is equal to, we'll have the force due to actually a charge 2 on 1, we'll have it as F12. And the force on charge 1 due to a charge 3, we'll have it as F13. So basically, I regard that this is the parental charge and this is the daughter charge. This is the parental charge and this is the daughter charge. Now there is a need of generating the direction or indicating the direction of the force. What is the direction of force 1, 2? So the direction of the force 1, 2 will be based from the parental charge. So what is the parental charge? We have it as a charge 1. So this is the negative charge and this is the positive charge. What is the force that will exist between the two charges? Will be the attractive force. And what will be the direction of the force actually charge 1 will experience? The charge 1 will experience the force towards this direction. So that is given as F12. And since it is towards the positive direction, we have it as a positive F12. Now how about, let's say, F13? So this is the parental charge and this is the daughter charge. And the direction has to be from the daughter, actually has to be from the parental charge. So looking at the charge 1 as well as the charge 3, the charges are like charges and the force between them, it is the repulsive force. So what will be the direction of the force in which charge 1 will experience due to charge 3? The force will be towards this direction. It will be given as F13. So since it is towards the negative direction, we'll have it as a negative here. So this is the expression that corresponds to the net force acting on charge 1 due to the other charges. And if we could have had some charges here, we'd also do the same. We could have had, let's say, F1, 4, and sort of. And how about the expression for, let's say, F2 net? How can you have the expression for F2 net? Now we're looking for the net force acting on charge 2 due to the other charges. That will be given as F21 and also F23. Now let's look at the directions and give it out the signs of these charges. Now this is the parental charge that you should have to consider about. Now we have charge 1 as well as the charge 2. And these charges are actually analytic charges, and there will be the force of attraction between the two charges. Now what is the direction of the force a charge 1 will experience due to charge 2? And the force will be towards this direction. That will be given as F21. Now since it is towards the negative, we'll have it as a negative. How about F23? How about F23? Now it is between charge, actually it is between a charge, or actually charge 2 as well as the charge 3. And the two charges are actually analytic charges. And the force that will exist between them, it is the repulsive force. It should be attraction force. And what will be the direction of the force a charge 2 will experience due to charge 3? Now it will be towards this direction. Since it is repulsive, a charge 2 will experience being pulled towards this direction. So since it is towards the positive direction, we'll have it as a positive charge. Actually, it will be the positive force. So this is how the net force expressions will be expressed for these charges. And how about, let's say, F3 net? What would we say? Now F3 net will be the net force acting on charge 3 due to the other charges. That will be given as F31 and also F32. Now what did we say about the directions of the forces that we're talking about? F31, this is the parental active charge now, and 1, it is the daughter charge, and the direction has to be from the parental charge. So these charges are actually erect charges, and the force between them, it will be the repulsive force. So what is the direction of the force charge 3 will experience due to charge 1? Will be towards this direction. So that is F31. And since it is going towards the positive direction, we'll have it as a positive. How about F32? Now it is between, it is between charge 2 as well as the charge 3, and of which the force has to be from charge 3. Looking at the charges, there are no charges, positive charge as well as the negative charge. Will the force charge 3 experience due to charge 2 will be towards this direction or this direction? What did we say? So the force will be towards this direction. Now since it is negative, we'll have it as a negative. So keep that in mind. So that's the principle behind the superposition principle in one dimension for the system of the charges in one dimension. Let's say we have another system of the charges in a one dimension as well. Let's say this is charge 1, should be negative charge, and this is charge 2, let's say should be positive charge, and let's say this is charge 3, negative charge, and let's say a charge 4 should be, let's say, a positive charge, and this is charge 5, let's say negative charge. So try to come up with the net expressions, net force expressions on the following. Let's say F1 net expression. What will be that? And F2 net expressions. What will be that? And also F3 net expression. And what will be that? And also what is F4 net expression? what would be that? And let's say F5 net expression, and what would be that? And try to have that at your own time. And for the sake of realistic, we can have, let's say this is A, B, C, D, corresponds to the distance between charge 1 and charge 2 is given as that, and likewise you have those things. So let us see on how we can apply this context in the actually following examples and appreciate how it works. Let's say we have the system of the charges in one dimension. Let's say this is the charge 1, a negative charge, and basically it is given as 2.9. Let's say 2.9, let's say microcoulomb, and let's say this is charge 2. Let's say it is given as the positive charge. Now this is a negative charge, by the way, and now this is given as 3.87, let's say microcoulomb, and let's say this is charge, let's say 3, a negative charge is given as 1.5 microcoulomb, and let's say this is charge 4, and that is given as a negative charge. This is negative, and let's say it is given as negative 0.5, let's say negative 5 microcoulomb as well. Let's say that is the case, and say the distance between charge 1 and charge 2 is given as, let's say, 2 meters, and here as well is given as 2 meters, and here is given as 1.5 meters. Now, what is the net force acting on charge 1 due to the other charges? What is the net force? That is F1 net, and that due to the other charges. Now have it as F12, F13, and F14. And let's see the signs corresponding to the directions of these forces. Now F12 corresponds to the force on 1 due to charge 2. And this is the negative charge, and this is the positive charge. It is the attractive force, and the direction will be towards this direction. That will be given as the positive direction. Hence, this is the positive force. And how about F13? That is the force on 1 due to 3. And the charges are actually erect charges, and the force between them, it is the repulsive force. And what is the direction of the force? Will be towards this direction. Now in that case, we'll have it as a negative. And how about F14? So looking at the charges, the erect charges, and the force between them will be repulsive force, and the direction will be also the same direction. Mind you, the direction of the force is being generated from the parental charge, so that will be given as a negative as well. Then how should we go up next? Then we are going to calculate what is force 1, 2 using the Coulomb's law. What will be that? Using the Coulomb's law, we have electric constant times the magnitude of the charge 1 and also the magnitude of the charge 2, and divided by the separation distance square. And what will be that? So in this case, we know that the value of the Coulomb's constant is given as, and that should be 8.99, and that is times 10. Let me have this at this point. That is F12. That is given as 8.99 times 10 to the positive 9, and the times what is the value of charge 1. We have it as, now since this is the absolute value, we would disregard the negative, so have it as 2.9 times 10. What is micro? It is -6. The times what is charge 2? We have it as 3.87 times 10 to the power -6, and that is divided by what's the separation distance between the charges? We have it as 2 meters to the power 2. And let's see how the calculation will be done. So I recommend that at whichever the aspect, you should have to put those in brackets, and basically it brings about the reliable results. So we have 8.99, and that should be times 10 to the power, and that should be 9 in a bracket. That is 2.9 times 10 to the power somewhat -6, and at times we have 3.87. Should be that 3.87. Should it be that? Yes. And that times 10 to the power -6. In your case, avoid doing all these things once. Just have to start little by little. So on top here we'll have, let me take it out here. So on top here we'll have F12. That will be given as 0.00, let's say 1, divided by what's the separation distance square? We have it as 4 in newtons there. So we'll have divided by 4, and that is, now we have it as 0.025 newtons. That is F21, and keep it safe. Let me take this one out. That is F12. That is 0.025 newtons. And let's go ahead and calculate what is F13. And this is being done upon having written your expression for the net force. Then let's go ahead and calculate what is F13. So F13 will use the same principle. That is 8.99 times 10 to the power +9, and times what is the charge 1? That is 2.9 times 10 to the power -6, and times what is the charge 3? We have it as 1.5 times 10 to the power -6. We'll have that divided by what's the separation distance between charge 1 as well as charge 3. Now the separation distance is given as a 4. We'll have 4 to the power 2. Of course that will be 16. How should we have the calculations there? So principle remains the same. We have 8.99 times 10 to the power +9, and at times 2.5 times 10 to the power -6. That would be -6, and at times 1.5 times 10 to the power, and that should be -6 as well. That would be that. Then I divide by 16. What would be that? So now we have it as 0.002. That is a force F13. That is 0.00, I'd say 0.00 should be 24 after the neurons. Of course, you can have 0.02 neurons, can be that. Anyway, then let's calculate what is f f1, let's just say f14. What is f14? Now in this case, principle remains the same. f14 also been given as 8.99 times 10 to the power positive 9. In the terms, what is the charge 1? We have it as 2.9 times 10 to the power negative 6. And what is the charge 4? That is 0.5 times 10 to the power negative 6. And that divided by, what is the separation distance? We have 1.5, actually 5.5, and that to the power 2, of course. Since we just have to add the 2, like that, should be 3. Then we have it as a 5.5 actually meters. So distance has to be in meters. So given in whichever the unit, it is a humble duty to convert that to be in meters. So let's see on how we can be able to calculate those. That is, we have 8.9, should be in brackets. 8.9 times 10, to the power positive 9. So during the typical exams, that value is always being given. It's a constant value. So times 10 to the power negative 6. And that times 0.5, times 10 to the power also negative 6 as well. And that is so in this case we'll have it as being given as f14 is given as a 3 point, should be 4 point. You can also verify these calculations. So 4.31 times 10 to the power should be negative 4 neurons. So that's how you should have to understand about the Coulomb's, actually the Coulomb's law. You should be able to familiarize yourselves with how to operate the calculations to do with the Coulomb's law. Then now we're going to substitute in the expression. We have f1 net as a vector. We'll have it as, now what is f12? We have it as 0.025 neurons. Now since this is in x direction, we'll have it as I, because we are should be in the x-axis. That is, we use I. The negative, what is f13? 0.0024 neurons. That is also I as well. And we have minus, that is 4.31 times 10 to the power negative 4 neurons. That is also I. Then you will have to add up those, since they are in the same dimension. Can be added as well. Of which we can have it as, what will be that? Suggest. So which means we'll have it as 0.25. I should say 0.025, and that plus, that is 0.0024. The plus of, now we are subtracting, the other ones are subtracting, so we need to indicate the way that one is. We have 0.025, then minus 0.0024. minus 4.3, that is 1 times 10 to the power negative 4. So now F1 net as a vector will be given as 0.022 actually newtons, that is along x-axis, that is high in that way. So this is how it will be in a vector notation in terms of a vector. But now, what is the net force? Now net force will be given as F1 net as a magnitude, will just been given as 0.022 newtons. So this is as the magnitude and this one as a vector. Had it been that F1 net was a negative, it means we could have had as a vector being given as that. Now a net force as a magnitude could just be given as the positive value. So keep that in mind. And at your own time, try also to find out what is F2 net and what is F3 net. So try that at your own time. Take note of that. Now let's consider the system of the charges also in one dimension. But now let's say we have the system of the charges. Let's say this is, I'd say, charge 1, and let's say this is, let's say, the charge 3, given as the negative charge, and this is the positive charge. And let's say the distance between the two charges, let's say the distance between the two charges, I have to say it like this. Let's say the distance between the two charges is given as this. Let's say this is the distance given as, let's say, 2 meters. And assuming that we have another charge 2, assuming that we have another charge, actually we have another charge, let's say charge 2, let's say in the between the two charges, let's say given as charge 2, and let's say it is given as a negative charge, of course, can be that. And let's say from the origin or from the reference point, which is on charge 1, actually a charge 2 is at some distance. I would call it as a distance x. Let me have it this way. I'll call it as, let's say, distance x. Now the point of interest is, what is the position in which charge 2 has to be in order to experience the net force due to the other charges as a cell? What is the position in which charge 2 has to be experienced, has to be pressed in order to experience the net force acting there as cell? In other words, what is the value of x that will make actually a charge 2 to experience the net force being given as cell? So that is the principle behind the system of the charge that will experience the net force acting there due to the other charges as cell. So Stromer principle remains the same, in the sense that F2 net is given as, what is the formula we have? F21 and also F23. And let's see what are the directions of the vectors. and that corresponds to the signs of the charges. Now what will you say? Well, F1, the two charges are unlike charges, and the force they experience, the force charge 2 will experience, it will be the force towards this direction, so it will be negative. And how about F23? Now these actually charges, they are actually like charges, and actually this charge is going to experience the force that will go towards, let me have this one as the positive charge. This is a positive charge. Now the force in which charge 2 will experience will be the attraction force, that will be towards this direction. So since it is towards the positive direction, will be given as the positive. Now since we are saying the net force on charge 2 is given as L, we'll have L is equal negative F21 plus F23. Of course this is the same as F21 is equal to F23, as you can see. But now let's ignore the directions as the vector. Let's ignore the directions as the vector. So in this case, using the Coulomb's law, what is F21? Now F21, it is the force charge 2 experience due to charge 1, and that will be given as Ke. We call it as just K or Ke. It represents the same Coulomb's constant times the magnitude of the charge 2 and times the magnitude of the charge 1. Now what is the distance between the two charges? We have it as x. That is the distance. Now that is the distance between the two charges, which is equal to K times, now we still go over again, that will be given as, a charge 2 times the magnitude of the charge 3. So what is the distance between the two, which is given as this? You observe that it will be given as 2 minus x. We'll have square here and also square here. In this case, we'll be able to find the value of x that satisfies the condition in which f net here will be given as L. So this and this will cancel, and this and this will cancel. What will only remain is this. What will only remain is charge 1 divided by x squared is equal to charge 3 divided by 2 minus x. In that way, then you can be able to find the value of x using arithmetic concept that will correspond to have the net force acting on the charge between, that is charge 2, as to be 0. So keep that in mind. So at your own time, try to have this. What if we have, let's say, this is charge 1, a negative charge that is given as 2.56, let's say, nanocoulomb, and we have, let's say, charge, let's say 3, that is a positive charge. It should be a positive charge that is given as 1.6 nanocoulomb. And let's say the separation distance is given as, let's say, 1.5 meters. So where do you expect a charge, actually a charge 2, which is a negative charge, to be pressed in such that the net force acting on it due to the other charges is 0? Mind you, whenever the system experiences the force net being given as 0, it means that system is at equilibrium. Where do you expect charge 2 to be at equilibrium? That is the point of interest. Where do you expect charge 2 to be at equilibrium? That is the point of interest. Find the value of x there. That's what we're looking for. So that's how you should have to understand about the superposition principle in actually one dimension. And what if we have this case as well? Let's say we have, this is the Cartesian plane, and of course this is x-axis, and let's say the distance from the origin to some charge, let's say charge 3, which is a negative, that is given as 10.9 nanokilo, is given as 2 meters. And we have, let's say, charge 2. Let's say we have a charge 1, which is a positive charge, that is given as 2.7 nanokilo. Let's say this is negative charge in that way. Now where do you expect, and let's say this is 3 meters. Now where do you expect, a charge 2 has to be pressed? Let's say in this case, this is the position of charge 2. Let's say it is given as the positive. What is the distance in which charge 2 has to be in order, or what is the position charge 2 has to be from charge 1 in order to be at equilibrium? In other words, in order to experience the net force being given as 0. So try to have that at your own time. So that's how we actually should have to understand about the superposition principle, and therefore the electrostatic force in one dimension. So don't forget to subscribe to this channel, and for you to be updated for every content that has been created and that is best for you. Thank you.